Consider an experiment of tossing a coin. Let the occurrence of a head be considered a success and the occurrence of a tail a failure. Thus, the probability of success is 1/2, which remains the same for any number of trials. This implies that the outcome of each trial is independent. Hence, the trials are Bernoulli trials. Many a times, we wish to know the probability of a certain number of successes in Bernoulli trials. The outcome of having one success in one trial is S. The outcomes having one success in two trials are SF and FS. The outcomes having two successes in three trials are SSF, SFS, and FSS. It seems easy to know the possible outcomes associated with a less number of trials. However, it becomes quite tedious and time-consuming as we go for higher number of trials. Now, let's derive a formula to avoid this time-consuming calculation. Let X denote the number of successes in a trial, where a success denotes the occurrence of a head. Let P and Q denote the probabilities of getting a success and a failure, respectively. Let's begin by tossing the coin once. The possible outcomes are S and F. Here, the number of successes is either 0 or 1. Therefore, the probability that X can take the value 0 is the probability of the occurrence of a failure, which is Q. And the probability that X can take the value 1 is the probability of the occurrence of a success, which is P. So, the probability distribution of X is as shown. Next, let the coin be tossed twice. In this case, the possible outcomes are SS, SF, FS, and FF. Here the number of successes is 0, 1, or 2. Therefore, the probability that X can take the value 0 is the probability of the occurrence of FF, which is Q squared. The probability that X can take the value 1 is the sum of the probabilities of the occurrences of SF and FS, which is 2PQ. The probability that X can take the value 2 is the probability of the occurrence of SS, which is P squared. Therefore, the probability distribution of X, when the coin is tossed twice, is as shown. Now, let's consider the case when the coin is tossed thrice. The possible outcomes are SSS, SSF, SFS, FSS, SFF, FSF, FFS, and FFF. The number of successes in this case is 0, 1, 2, or 3. Therefore, the probability that X can take the value 0 is the probability of the occurrence of FFF, which is Q cubed. The probability that X can take the value 1 is the sum of the probabilities of the occurrences of the events having one success, which is 3pq squared. The probability that X can take the value 2 is the sum of the probabilities of the occurrences of the events having two successes, which is 3p squared q. The probability that X can take the value 3 is the probability of the occurrence of SSS, which is p cubed. Therefore, the probability distribution of X when the coin is tossed thrice is as shown. Observe that the distribution of x for the Bernoulli trials are similar to the binomial expansions of q plus p raised to the power of n. For the first trial, the power is 1. For the second trial, it is 2. And for the third, it is 3. Also, the probabilities of 0, 1, 2, or 3 successes are the corresponding first, second, third, and fourth terms of the respective binomial expansions. This result can be extended to n Bernoulli trials. In an experiment of n Bernoulli trials, the probabilities of 0, 1, 2, and so on till n successes are the first, second, third, and so on till n plus 1th terms of the expansion q plus p whole raised to the power n. The terms of the binomial expansion of q plus p whole raised to the power n are shown. This probability distribution of a random variable x is called a binomial distribution. Thus, the general formula for the probability of a given number of successes is given by the probability of x successes, or the probability that x can take the value x, is ncx into q raised to the power n minus x into p raised to the power x. This is denoted by p of x. Now, ncx can be written as n factorial divided by x factorial into n minus x factorial, where x is equal to 0, 1, 2, and so on till n, and q is equal to 1 minus p. Here, p of x is known as the probability function of the binomial distribution. Now, let's apply binomial distribution to find the probability of getting 2 heads if a coin is tossed 6 times. Let the event of getting a head on tossing a coin be a success, and the event of getting a tail be a failure. Let x denote the number of heads obtained when a coin is tossed 6 times. Let p and q be the probabilities of getting a head and a tail, respectively, if a coin is tossed once. Therefore, p is equal to 1/2 and q is also equal to 1/2. Since the coin is tossed 6 times, the number of trials is equal to 6. Therefore, x has a binomial distribution with n is equal to 6 and p is equal to 1/2. The probability that x is equal to x is given by the formula here. Thus, the probability of getting 2 heads, or the probability that x can take the value 2, is equal to 6c2 into half raised to the power 6 minus 2 into half squared. This is equal to 6c2 into half raised to the power 6. On simplification, we get 15 divided by 64.